In this review, we're going to talk about hypothesis tests. So in statistics, hypothesis tests are a way to determine if an observed difference is significant or simply just due to chance. And when we say chance, we really mean the chance of which sample we picked. So for the steps of any hypothesis test, first you always have to decide which test is going to be right for your situation. So if you want to test like something about a population mean, you might want a z-test or a t-test. In this class, we're going to be doing tests for regression. So we'll use like t-tests for individual predictors, we'll use an f-test for overall fit. We'll have a lot of different tests and you have to find the right one. Then you talk about assumptions. So most tests have conditions or assumptions that have to be met for your results to be accurate. If the assumptions aren't met, then any p-value you get at the end is just going to be worthless, completely inaccurate. You have null and alternative hypotheses. So h with a 0 is our null hypothesis. That's kind of like our boring, our status quo, nothing interesting. The alternative hypothesis with h with an a is usually what you actually want to show. Your test statistic, you'll calculate some value from your data, and then most tests will have some kind of degree of freedom depending on which test it is. Then for the p-value. The p-value, we assume that our test statistic follows some probability distribution. Now this is where those assumptions up above come in, because if your assumptions aren't met, then the probability distribution isn't going to line up with what you think it should be. So we use the probability distribution to find the p-value, which is going to be the area under the curve in the tails. So tail or tails. And the p-value is going to be the probability of obtaining our sample statistic, or one even more extreme, that means like even farther out on the tails, if the null hypothesis were true. Basically, extreme means far away from what we'd expect if the null were true. You're going to reject or fail to reject the null hypothesis. So if your p-value is small, if it's less than alpha, we call a small p-value, we reject the null, that means we have evidence for the alternative, and the smaller the p-value, the stronger the evidence we have against the null hypothesis. Whereas if your p-value is bigger than alpha, that means you have a big p-value, fail to reject the null hypothesis, and that means we didn't find enough evidence for the alternative. Note, this is very important, we do not say that we accept the null hypothesis. Even at this graduate level, we still see students every semester trying to say that. You can't say that. Okay, so it means we didn't find enough evidence to reject the null, that means we didn't find enough evidence for the alternative, but we don't say we accept the null. We're never looking for evidence for the null, we're always looking for evidence against it, so you can't say that you accept the null. And the conclusion, you always write out a conclusion in sentence form explaining your results of what you got. So let's look at the one sample t-test for population mean. We don't have to do that in this class, but it's a good practice of how hypothesis tests work. So let's see, the conditions, if our population is normally distributed or the sample size is large, of at least 30, then your null hypothesis will be that your population mean mu equals some hypothesized value. Mu naught we'll call our hypothesized value. Our test statistic t is equal to our sample mean minus that hypothesized value over s over the square root of n. Degrees of freedom are n minus 1. And the p-value is going to be the area under the t-curve, and that's either going to be in the left, right, or both tails. What that is depends on your alternative hypothesis. So let's look at like what it would be with our value from our next one. I'm just going to say 78 just so I can put a number and it makes it look a little bit better. So if your alternative is you think that the mean is less than 78, what you want to do is find your t-value. It will probably be negative and you shade to the left. If your alternative is you think that the mean is greater than say 78, then you'll find your t-value and shade to the right. So greater than right, less than left. If you think that your alternative is that the mean is not equal to 78, so that means you don't really know if it's higher, you don't really know if it's lower, you don't really care, you just kind of think it might be different. Well, then what you'll do is you'll shade both tails. You might end up with a negative t-value or a positive, so sometimes you'll put like absolute value of t. And shade, again, both tails. So let's say your client believes the true population mean mu of MDU players in 2001 and 2002 was greater than 78 inches. Let's use our sample of 10 basketball players to evaluate his belief. You can assume the heights are fairly normally distributed. So that normal is important, that means our condition is met. And it didn't tell us what alpha we can use, so if you don't have a reason to pick a specific alpha, we'll just always go with the default of 0.05. In our sample, we had 10. Our sample mean is 79. So we can clearly see like our sample mean of 79 inches is greater than his hypothesized mean of 78 inches. But is that difference significant, or was it just due to chance? Was it just due to which sample we picked? So is that enough evidence to say, oh, I think the population mean must be greater than 78 because our sample mean was? Or did we just kind of pick a slightly higher sample and that difference was just due to chance? So first step is always, let's write the null and alternative hypotheses. So the null, we'll do the H with the 0, and we're comparing it to a hypothesized mean of 78. So we're going to compare it to 78. So we'll do, for the null, we'll do an equals. For the alternative, we'll do an HA, and we'll do, let's see, he thinks it's greater than 78. So greater than 78, that's the one he's interested in checking. Our test statistic is going to be T equals X bar minus mu naught over S over the square root of N. So our sample mean is 79 minus our hypothesized mean is 78 over the sample standard deviation of 3.5 over the square root of the sample size of 10. That should give me about 0.903. We need to know our degrees of freedom. That's supposed to be n minus 1, so 10 minus 1 is 9. And for my p-value, I always draw a picture. I had t equals 0.903. This is a greater than alternative hypothesis, so I'm going to shade to the right. And I need to look that up. So what we're going to do is come back to our t-table. We have 9 degrees of freedom. And we're looking for a value of 0.903. That should be somewhere about here, 0.903. So that means my p-value is between 0.10 and 0.20. So I could say between 0.10 and 0.20. Okay, so I can use SAS to find this exactly. So our p-value, we could just say it's between 0.10 and 0.20. Or if I use SAS, I can say the exact p-value is about 0.195. So that's our p-value. So if our p-value is 0.195, is that bigger or smaller than alpha 0.05? That's going to be bigger. So it's going to be bigger than alpha equals 0.05. So we're going to fail to reject our null hypothesis. And that means we did not find evidence that the population mean height for all the basketball players is greater than 78. So it's not saying, we don't say that we found evidence for the null. We don't say that we found evidence that it is 78, but we're saying we didn't find evidence, or we didn't find enough evidence that the population mean height of all the basketball players is greater than 78. Okay, so we failed to reject, we didn't find evidence. Now this next little part, I didn't include it in the notes, so you might want to flip the page or see if you can squeeze it in. So we might want to ask, was our hypothesized mean of 78 in the confidence interval we found earlier? So previously, in the other video, we found a confidence interval was 76.5 to 81.5. So that's what we thought was a plausible region for our that's what we thought was a plausible region for our population mean height. So we think any value between 76.5 to 81.5 could be very plausible for our population mean. Well, if we have a hypothesized mean of 78, and if 78 is inside this confidence interval, that would mean that 78 seems fairly plausible. Okay, so we could say that because the hypothesized mean of 78 was in our 95% confidence interval, that means it's going to be plausible, it's believable. So we could say that for like a two-sided hypothesis test, instead of actually doing the entire test, we could just say, well, 78 was in our confidence interval, which we already found, so that means we failed to reject the null, and we could have just skipped to that final step. So hypothesis test give us the same information as confidence tests if you want to use this trick. So if your hypothesized mean, the value in the null hypothesis, so the hypothesized mean, that's what we call mu naught. If that's in the confidence interval, then it's plausible and we fail to reject the null. If the hypothesized mean is not in the confidence interval, it's not plausible and you reject the null. So that's just kind of a trick. You can just use the confidence interval to do your whole hypothesis test. Now, occasionally I might have a student that's really paying attention and they might say, oh, well, this was just a one-sided t-test, but our confidence interval had two sides. Well, that's okay. The reason why is it's just more conservative. Yeah. Because if you think about it, when we had our confidence interval, it had 95% in the middle, and that would be like 2.5% over here, 2.5% over here, and if it's in the middle, we fail to reject, and if it's over here, we reject. So basically, if you have a two-sided confidence interval, then it's really doing a hypothesis test, or a one-sided test, at alpha equals 0.025. And doing a smaller alpha is never going to hurt you. That's just more conservative. So you could switch to like a one-sided confidence interval and you could draw it out and say, okay, I'll put 95% here and 5% here. And if it's over here, fail to reject. And if it's not in the tail, reject. So you could do a separate confidence interval. We do know how to do one-sided confidence intervals, but you really don't need to. In fact, you'll find a lot of times in these higher classes that we don't really worry about if our test is going to be one-sided or two-sided, especially once we start looking at having multiple predictors in our linear regression. You might do like 20 or 30 hypothesis tests at one time, and you're not really going to want to have to check each of those to say, oh, was that supposed to be left or right, and figure that out. So we just do two-sided, which is more conservative. It just makes our p-values even higher than they're supposed to be, and that's always okay. Because we just want to make sure that we don't reject when we're not supposed to. So we're okay being a little more conservative and making alpha a little bit smaller. That's not going to hurt us. Okay, last page. So statistical significance, first of all. If our p-value is as small or smaller than alpha, we say the data is statistically significant at level alpha. To understand this, we might want to back up just slightly and look at what does alpha mean. So if alpha equals, say, 0.05, that means if we drew millions of samples and did a hypothesis test each time, then each one gives different results. That's why sampling distributions are so important. Then we would only do a test and accidentally reject a true null hypothesis only 5% of the time. So that's why on the previous page where I'm saying, okay, well, you might make alpha a little bit smaller. That just means, well, then we only accidentally reject a true null hypothesis only 2.5% of the time. That just makes it even better for us. Okay? So statistically significant means if we get a p-value that's small or smaller than alpha, we think is statistically significant. We're saying we're pretty sure if our results would only happen, say, 5% of the time when the null is true, then we're fairly sure that we didn't make a mistake and the null was probably false. Or if we get a p-value of like 0.0001, then we're like, we had a really, really tiny % chance of getting this data if the null were true. And so like we only have a really tiny % chance of rejecting it when we're not supposed to. So we're pretty sure that the null was false. So if we choose alpha equals 0.05, we're requiring that the data give evidence against the null so strong the data would happen no more than 5% of the time when the null is true. So our common levels of significance are alpha equals 0.10, 0.05, and 0.01. These kind of just depend on what field you're working in. But 0.05 is what we do almost every time. Okay, so back for our basketball heights, was our result statistically significant? Well, if you remember, our p-value was 0.195. That is a big p-value. And we failed to reject So no, these are not statistically significant. Let's look quickly at the types of errors. So you can have a type 1, type 2, or a type 1 or type 2 error. A power is slightly different. So a type 1 error is when we reject a true null hypothesis. So it was true, but we accidentally rejected it. The type 2 error is, well, we accidentally failed to reject a false null hypothesis. So the null was false, we're supposed to reject it, but we accidentally said failed to reject, and we didn't reject it. So this is a little table if it helps you. So if the null is true and you fail to reject it, that was good. But if the null is true, but you accidentally reject it, that's a type 1 error. If the null is false and you don't reject it, then you have type 2 error. If the null is false and you do reject it, good job. And just as a remark, the probability of a type 1 error is equal to the significance level alpha. Well, that makes sense because we said if alpha equals 0.05, we only accidentally reject 5% of the time. So that was the probability of the type 1 error. For power, the power of the test is the probability of rejecting a false null hypothesis. You want to reject a false null hypothesis. That's a good thing. So power is good. Notice that power is going to be 1 minus the probability of a type 2 error. Because we said the null is false, so you can either make a type 2 error or have a correct decision. We want the correct decision, so it's 1 minus the probability of the type 2 error. So small probability of a type 2 error leads to greater power. We want good power. We're not really going to calculate anything with power in this class. Okay, for our basketball heights, what would each of these be in context? So let's come up here so I have a little bit more room. So for type 1 error, we said type 1 error is when null is true and reject. So I'm going to write like this. I'm going to say I'm rejecting the null, and the null is true. Okay. And then I'm going to put what each of those would be in error. In context, this kind of helps me get it right. So for our basketball heights, if you remember, the null was that mu equals 78. The alternative is that mu is greater than 78. So if we reject the null, that means we're going for the alternative. So we think that the mean is greater than 78. But the null was really true, so this part was true. So really, mu equals 78. So let's write that down here in words. Okay, so a type 1 error is we decide that the population mean is greater than 78. But really, it is 78. So let's do the same thing for a type 2 error. So for a type 2, we're going to fail to reject the null, but the null was actually false. So if we fail to reject, then we say, okay, well, it might still be 78. So we think it might be 78. Okay, but the null was actually false, so that means this was actually true, but mu is greater than 78. So if we write that, that means we decide that the population mean might be 78, but really it is the mean is greater than 78. Okay, power is you do it correctly. So it's you do it correctly and the null is false. So if the null is false, the mu is greater than 78. So really the mean is greater than 78. And we decide the mean is greater than 78.